Hey guys, this is chapter 7, and we're going to start with section 7.2, equations of state for real gases and their range of applicability. 7.1 is basically an intro, there's no meat there. So we're going to start out looking at a couple of equations that we can use for real gases. The van der Waals, which you've seen before, and the Redlich-Kwong equation down here. Both of these equations have two parameters that depend upon which gas is being dealt with, A and B, and they both mean the same thing in each of these equations. A is measure of how strong the attractions are between the particles. B is a measure of how much volume they take up. While they do represent the same thing in both equations, they have different values, numerical values, depending upon which equation. So A for carbon dioxide in the van der Waals equation is a different value than A for carbon dioxide in the Redlich-Kwong equation. So in these graphs right here, look at the top graph right here. This is at 426 Kelvin. The red line represents the behavior of carbon dioxide gas from the ideal gas law, predicted by the ideal gas law. The blue is the Redlich-Kwong equation. You can't really see it, but right underneath it there's a purple one, which is the van der Waals. Black dots are experimental data, basically, so it's the real behavior. And everything lines up pretty well. Van der Waals and Redlich-Kwong do a little bit better than the ideal gas law, but it's still pretty good. But when we lower the temperature in the second graph here down to 310 Kelvin, now we see a dramatic difference. The ideal gas law does not really come even close to the behavior of the actual gas, but the two other equations do a lot better. That kind of makes sense because if we go back and think about the kinetic molecular theory, we said the kinetic molecular theory, which is the tenets of the ideal gas law, says that the particles don't interact and they don't take up any volume. So at higher temperatures, that would be a good approximation because there's enough energy to overcome the attraction, so the attractions or repulsions aren't going to make any difference really. Likewise, when they're moving on average faster at this higher temperature, there's more empty space, there's more room between the particles, and so their actual volume becomes less important. But when we get down here, 310 Kelvin, about 37 Celsius, we see a difference. There's quite a few other equations, but another equation that we will deal with is called the Virial equation of state. And all this is a power series expansion in 1 over the molar volume. This M means the molar volume right there. Back when I showed you the van der Waals and the Redlich-Kwong equations, I had N in there. I didn't use the molar volume. We will in a minute. This one does. And in the Virial equation of state, this B, which is a function of T, temperature, C, function of temperature, and so on, are called the virial coefficients. B is the second virial coefficient, C is the third, and so on. Normally, as a practical matter, we stop at the second virial coefficient, basically because it's experimentally difficult to get values for the third virial coefficient. Another thing about this series, guys, is that this does not converge at high pressures because high pressures means the molar volume gets small. As the volume goes to 0, this series explodes, it doesn't converge. We can get some useful information about the behavior of the gas from the value of the second virial coefficient. If it's negative at some temperature, that means that the attractive part of the potential is more important at that temperature. If it's positive, the repulsive part's more important at that temperature. For example, if you look up the second virial coefficient for a krypton at 500 Kelvin, it's negative 7.75 centimeters cubed per mole. But at 600 Kelvin, it's positive 1.78 centimeters cubed per mole. So at this higher temperature, the repulsive part of the potential is more important. It dominates, sort of. All right, so let's look at this graph right here, guys. What this is a PV diagram, pressure versus molar volume. And each of these lines represents an isotherm, meaning that the temperature is the same along each of these lines. Couple of things. The dashed line is the behavior predicted by the ideal gas law. at 334 Kelvin, and this is all carbon dioxide. So if we look at this, a couple things we get from here. First of all, these straight regions in here actually do not come from the equations, the Virial, not the Virial, the van der Waals or the Redlich-Kwong. They're called something called Maxwell constructions, and we'll talk about them in a minute. There's also some funny behavior that we're not shown in this graph that comes from the equations, but it does. The thing that, those two equations do much better than the ideal gas law is they predict liquefaction, that it becomes a liquid. So in this graph right here, the blue region is where it's a liquid, the yellow where it's a mixture of the gas and the liquid, and out here it's just a gas. So let's see, let's look at the isotherm that's 258 Kelvin. And we have 4 points here, A, B, C, and D. Before about right here, which is like a little over a third of a liter for the molar volume, as we decrease the volume, the pressure gradually increases, which makes sense because gases are compressible. In this region right here, the pressure does not change, it stays constant the whole time. But once it's all been converted, the carbon dioxide has all been converted from a gas into a liquid, if we try to squeeze it anymore, if we try to decrease the volume, the pressure just shoots way up because liquids are not very compressible. So you squeeze it and the pressure is going to just shoot right up. And we can think about this behavior if we think about this taking place inside of this cylinder with a piston. So at A, right over here, it's all gas. We start decreasing the volume, pressure goes up a little bit. Good. Once we hit B, we're inside this region right here. We have some liquid and some gas, which are in equilibrium. So as we go from B to C, we still have gas and liquid in equilibrium. The pressure doesn't change. Just pressing this gas and squeezing it, making it into a liquid. But once we get past this point right here, up to D, now this is where the pressure starts shooting way up because it's all liquid and liquids are not compressible. One other thing about this particular isotherm here, this temperature is what's called the critical temperature. And this is the temperature at which, at any temperature above this temperature, there is no liquid, well, definitely not any solid either. Doesn't matter what the pressure is, it's all gas. Well, actually, it's what's called a supercritical fluid. It's not a gas, it's not a liquid, it's something kind of cool in between. So what happens is, as you start increasing the temperature, the pressure at which this line is flat starts going up. The pressure at that point, by the way, is the vapor pressure of that gas or the liquid. So as we start increasing the pressure, we don't hit the vapor pressure until higher temperatures. Until we get to the critical temperature. Above that, it's all supercritical fluid. So as we start increasing the temperature, going up these isotherms, the density of the liquid becomes lower, less dense, and the density of the gas becomes higher. In the supercritical fluid region, it's neither a gas nor a liquid. It's a supercritical fluid, and its density is between that of a gas and a liquid. It has some pretty cool properties. We're going to see that in a later chapter. All right, so what we're going to do now, is we're going to see, this is pretty cool, we're going to see how we can get expressions for the van der Waals coefficients A and B. Works exactly like this for the Redlich-Kwong equation. So that's our goal. So what we want to do is we want to get A and B in terms of easily measurable values. It ends up that the molar volume at the critical point is not that easy to measure accurately, whereas the pressure and the temperature are, the critical pressure and the critical temperature. So our goal is going to be to get A and B, the coefficients, in terms of constants and critical pressure, critical temperature. So let's start with the van der Waals equation. There it is in terms of molar volumes. The N is not there because this is 1 mole we're assuming, so the N is 1. Remember at the inflection point, No, actually, let's do that. I don't think I said that. So at the inflection point, so this critical temperature right here, there's one point where it goes from being concave up to concave down. That's the inflection point. At that point, the first derivative is equal to 0, and so is the second. So we're going to use that property. So taking the first derivative, the partial of the pressure with respect to the molar volume at the critical temperature, we get this expression right here. Now, remember, notice that T is the critical temperature because we specified that over here. If we rearrange this, solve for this RTC, so basically bring this whole thing over the other side there, make it positive, multiply through by this expression right here, we get this. And we'll see why. Now let's do the same sort of thing with the second derivative, the second partial. So the first partial is this, the second partial is the partial of this with respect to the volume. And we get this. Real quick note, guys, if you're looking at the textbook, they have a sign error. They have a positive sign here. It's negative. Anyway, do the same thing, rearrange this, solve for RTC. We get this expression right here. Now, the thing is, guys, we've got two expressions that are both equal to the same RTC, which means they're both equal to each other. If we do that, set them equal to each other, multiply through by the reciprocal of the left side, a bunch of stuff cancels, right? We get the stuff in parentheses squared here, cubed here, so all but one cancels here. Get the molar volume. Notice we've got the C here, right? That means we're now at the critical point, the critical volume, critical pressure, critical temperature, molar volume. Cubed here, fourth power here, they all cancel. Multiplying through by 2 VMC, we get this. Can solve this for like this. We see that something pretty simple. The molar volume at the critical point is equal to 3 times B, which if we could easily measure the molar volume at that point, we would have B. But it ends up it's not that easy. So we're going to get A and B in terms of the other parameters: critical pressure, critical temperature. All right, so we're going to take this expression we just got, substitute it into our first partial. This is our first partial. We got that. Substituting for VMC, 3B. 3B minus B is 2B, right? So we get 2B squared here. This becomes 3B cubed. And we get 8A over 27RB for the critical temperature. So we're almost there, but we have two things here that we want, A and B. So now, take these two things that we have, substitute both of these into the van der Waals equation. So TC here, we replace with this. All the VMCs become 3Bs, and we end up getting, this is a 9 here, this minus that, which ends up being just the critical pressure equal to A over 27B squared. Almost there. So rearrange this, solve for A equals critical pressure times 27B squared. Substitute that into A for our expression we got for the critical temperature, and now we have it just in terms of B. So we can rearrange this, and now we get something really nice. B is equal to R times critical temperature over 8 times the critical pressure. Two things that we can probably look up really quite easily and calculate B. Likewise for A, we substitute what we just got for B into here, and we end up with this expression for A. So for example, for carbon dioxide, the critical temperature ends up being about 304.13 Kelvin. Critical pressure is about 73.75 bar. So if we substitute those values into both of these guys, just like this, we end up getting A is 3.657 liters squared, bar squared per mole squared, and B 0.04286 liters per mole, which if you look up these constants for carbon dioxide, that's basically what you're going to see. Now, where are these applicable? Well, it ends up that the van der Waals and the Redlich-Kwong equations fail at any temperature below the critical temperature. So in this graph right here, about 304 is a critical temperature. So down here, what we see is this is the van der Waals equation, but Redl-Kwong behaves similarly. These straight lines are Maxwell constructions. They don't come from the equation. If you graph the actual equation, you get these curves right here. And they do two things that don't mimic actual behavior. One is they don't have a flat line right here. Two, they do this little dip down here, which is not physical. We don't see that either. But above the critical temperature, we get, good behavior. So these Maxwell constructions, basically they're, okay, so the way you make that is you just, you make the area above the straight line and the area below equal. That's how you figure out where to draw it. And this gives good qualitative agreement with experimental behavior, but not so good quantitatively. But it's definitely a step in the right direction.